Good morning. This is our fourth session. And just to start off, I also wanted to do what I've been doing the other times. I just wanted to see if there's anything that stood out to you from last week. Last week finished up the HRU delineation in SWAT Plus in the QGIS plugin. And then we started moving over to SWAT Editor, and we'll continue on with that. I just wanted to see if there's anything hanging on people's minds before I dive in. You can also stop me as we get going, but before I start, is there anything anybody wanted to bring up? All right. I'll move on, but if there's any burning questions, I will do a brief recap. But if there's any burning questions, please just unmute and ask, because I can't always see raised hands when I'm showing the slides on the other screen. So don't be shy. Please jump in. So what we're doing today, we've been going through the overview of the concepts of what the model is doing behind the scenes, what is it actually calculating. And then we'll hopefully in the second half of today's session start to talk through some of the setup decisions for making models of the uMngeni water catchments. So today I want to give you a bit of an intro, like an overview on the climate inputs to SWAT Plus, because that's the next step we're going to do in the tutorial as well. And I'll do a recap of what we did in the GIS steps in the tutorials. That was delineating the streams, catchments and subcatchments, and HRUs. And then the next step in setting up a model is setting up the climate data and the parameter values and running the model and we'll go through that in the tutorial. And I will spend some time looking at the file structures and where the model stores everything and what the inputs and outputs look like. And then hopefully in the second half, or maybe the last third or so, we'll start looking at some decisions, particularly around land cover, that would inform how we would make HRUs for the uMngeni water case. If we don't get to that today, that's fine, because I do want to spend some time on the parameter, understanding what parameters go in for different land cover types, and I'll at least introduce this last topic a little bit to think about before next week's session. So before we jump into the tutorial, I just wanted to give a bit of background on how the climate data works, because I realize the tutorial doesn't show it very visually. So SWAT, I showed this slide before that the model data input needs include rainfall and atmospheric evaporative demand in terms of climate. So, and then we talked about these other elements, and we used catchment size, various elements of the topography, the land cover, and the soil types to make our HRUs, etc. But we haven't really talked about the climate piece yet. So the input data that it needs is rainfall and atmospheric evaporative demand. And that's a broad term, and different models, and different ways of looking at the water balance calculate actual evapotranspiration in different ways. But a typical way of doing it is using reference potential evapotranspiration, which you might have heard of before. And that's the amount of water that a plant could use if it was not water stressed, if it had all the water that it wanted. How much water could it use on a given day based on the climate? So based on the temperature, solar radiation, relative humidity, and wind speed would drive how much evapotranspiration, how much the plants would transpire, and also how much water would evaporate from the soil or an open water body. Then what happens in reality is that the plants and the soils, there's not infinite water in the soil, so it will actually transpire a little bit less than that because there's water limitations. But the reference point is how much it would transpire if there was no water limitation. So there's ways to estimate that if you use the temperature, the solar radiation, the relative humidity, and the wind speed. So that's what I mean by atmospheric evaporative demand. That's sort of how much would evaporate in those conditions, those climate conditions, if there was no water limitation. Then what the model goes in and does is look at how much water is actually available in the soil and works out what actually might happen. Obviously an estimate, but based on the vegetation that's there as well. So the climate inputs then are rainfall, and in this case, temperature, solar radiation, relative humidity, and wind speed. However, you don't always have all of that data, but if you have a full weather station, you would have temperature, solar radiation, relative humidity, and wind speed. If you don't have a full weather station, SWAT has some ways you can estimate it roughly from temperature using the minimum and maximum temperature. But the best option is to use all of those variables. Now, what I've done in the past is there are satellite data and estimates of all of those variables that are reasonably good. Rainfall, one does generally want to use station data. There are satellite estimates of rainfall, but it's much harder to estimate actual rainfall from satellite imagery because it's happening underneath clouds, and they're trying to estimate based on the temperature, like they can tell the temperature of the cloud and different properties of the cloud from the satellite imagery, but then they're estimating how much rainfall is actually falling out of the cloud. And so it's quite tricky. And also rainfall happens much more episodically. And if the satellite's not right over at that right point, it's a much more of an estimate. So it's more okay to use satellite data for these other features, and rainfall, we tend to want to use station data if at all possible. It's also much better to use station data for these other variables if you have it, but rainfall is the super critical one. So I will go, before I go on, are there any questions on that? I'm just going to talk to you about how then the data is input into the SWAT model for rainfall and for these other variables, temperature, solar radiation, relative humidity, and wind speed. So we went through the structure of the SWAT model before. So you break up the landscape, you have a stream network, and each panel unit has its own each stream unit, has a subcatchment. We also broke those subcatchments up into landscape units of upland and floodplain areas. And then we broke things up for the surface calculations into HRUs. And then the aquifers are the landscape unit based. But what we need is rainfall on these HRUs, because that's where the surface calculations are happening, where the rainfall is going to fall and where the evapotranspiration is going to happen. So what the model does is we input the time series data for 4-point locations of where weather stations or rainfall gauges or even temperature gauges might be. So I've put in some example ones. These aren't the points from the tutorial, but I just put in random points to show you conceptually what it does. So the idea is that you would have data for stations that are located throughout your landscape. Some of them might be outside of your actual catchment, like this one over here. And so you would give it the location, you give it the latitude and longitude point for these station points and what data is available for each point. And in this case, my yellow stars are imaginary weather stations. In this case, they're weather stations. And then this blue one over here is a rainfall gauge. So in my example, these weather stations would have all the data. They would have rainfall, temperature, relative humidity, wind speed, and solar radiation. And then at this point here, the blue point, it would just have rainfall data because it's just a rainfall gauge. So what the model does after you input this is it's going to work out to assign rainfall data in this case, it's going to work out which station is closest to which HRU, and it will assign the data from that station to that HRU. I've drawn these lines roughly, but it's kind of, you can see like this over here it's closer to this one. These ones are closer to this one. So it would assign that rainfall so that it doesn't always fall in line with the subcatchment boundary or anything. It would be which station is closest. And then if not all of your stations have all the data, it can assign different data from different stations so that every HRU gets all the data that it needs, but they can come from a different mix of stations. So to show you what that means, this is the distribution for assigning rainfall data from these points. All these points have rainfall data. But then when you're assigning temperature data, for example, this station over here is a rainfall gauge rather than a weather station. So it actually only has rainfall data. So then you would have to only use these two to apply to these for the temperature part. So you can do that. And then the way, sometimes we have gridded data sets from satellites or other products. In our case, we're going to be using HydroNet data, which some of you might have worked with before. I'm not sure. I know uMngeni Water has a subscription with HydroNet, so we're going to be using that. Now that's gridded data. So what we do there is we treat the center of every grid cell as though it were a station. And we'll input it there, and I'll go through that with you. But it's essentially like it was a station, because SWAT, the software we're set up to use stations. But you can use gridded data as though the center of every grid cell was a station. So then we'd have lots and lots of dots all over, and we'll input it like that. Is this making sense to everyone? I want to pause for any questions on this part. Okay, I see some thumbs up. Thanks. All right. So that was all I have in terms of presentation slides for this part before we go into the tutorial. So let me just escape and switch over to my tutorial. So I'm going to give everyone a sec to go into your QGIS and open up your project that you were working on to go through the tutorial for people who are able to keep working through it. And while you're doing that, I'm just going to recap a bit of what we did to get to this phase. And then we're going to shift over to that SWAT editor program, but it's to show you the flow, we'll open it from here. So you open up your QGIS project again, click on this SWAT plus. So I can open and close this just as it goes. And you can open that up. Does anybody have any troubleshooting questions actually on this part? Just do my recap so long, but if you have any, if you were going through and you struggled to get to this stage where we delineated the HRUs, and then we were moving on to this step 3 of editing the inputs and running SWAT plus, you can give a shout now, and I'm happy to help fix those. I know we did some at the end of last week. So a quick recap of what we did to get to this point by turning things off and on. We started by delineating our streams. Turn off the subcatchments there. So we used a threshold of flow accumulation to decide where it's going to start drawing streamlines and channel lines. And channels are the smaller ones and streams are the bigger ones. And then what it does is it delineates subcatchments at every intersection of a stream. So the bigger lines here. So we delineated subcatchments. And then I also added an additional point because let's say there was a monitoring point here that's not at a confluence between streams. It's along here. Maybe there's a weir or a long-term water quality monitoring point, or this also could be the outlet of a reservoir. We'll talk about reservoirs separately, but we can add other points manually along the streams. And then the other thing I did do was, just as an example, is I merged this branch here would have had originally had its own subcatchment. To demonstrate merging, I said merge this one a way you could do it if it was a really small one that you didn't want to consider separately. It will merge it with the next one downstream. So now this little branch here is merged in with this subcatchment 9. So I did a merging as well. And so then we have our subcatchments. We also went through a process of delineating landscape units. So I'll turn those on now so that we delineated a floodplain area. And there were different methods of doing that. And that's just a method of deciding what's lowland versus upland. You can base it on like a buffer around the stream, or the other methods include the topography, not just a standard distance away from the stream, but they look at, it's essentially looking at slope and the convergence of the topography to delineate a lowland around the stream. So is it flat and how much, is it flat and also how much land upslope leads into it? Gets used to delineate this. It's essentially like the opposite of a ridge. It's like turning, it's tricky. I find it tricky to put into words, but it's like as though you turn the topography inside out a little bit and you're delineating a ridge. That's the way that the algorithm works to do this. But you delineate a floodplain, and you can also, if you have another method to do your floodplain, you can prepare that input as a raster, a gridded GIS file with ones and zeros and put your own one in. You don't have to use the tools that they give you to make it if you have another way of making a floodplain delineation. So then we break up the subcatchments into these landscape units. And what you can also see is that there are landscape units for every channel unit. Right, so it's not just one, there's the floodplain, there's the upslope area and the floodplain, but it's also broken up for every time there's a confluence between a channel and another channel. And then it gets messy because see, there's this tiny little channel here that gets its own ones. Well, not messy, but there can be a lot of more landscape units than you might expect because it makes them for each little channel branch. So there are options to merge short channels in. And I think, oh yeah, these are full LSUs. And then I did some merging. Yeah, so there's the full and the actual. So if I turn them on and off, you'll see how many more there are. I merged in short little stream branches that were less than 5%, I think, of the LSU. Oh, sorry, of the subcatchment. So like this little channel branch here and here, these ones are not going to have their own landscape units now because we merged them. So that's the difference between these actual and full here. And if you use GIS, again, not everyone needs to be a specialist in all of these pieces, but it helps to understand what the model is calculating for where. But if you are someone who's going to be working with this more technically, it is, and if you use GIS more regularly, it is a good idea to have a look at some of these attribute tables of the files that it creates so you understand a bit what it's doing. So these are all going to have upslope and floodplain. The attribute tables, it'll give you areas, percent of the subcatchment, so on and so forth, average elevation of each one. So it calculates a lot of data for each one of these polygons for you, and that the model is going to use in its calculations. Okay. So then we've got the landscape units and the actual ones that we condensed. Somebody, I hear something. I'm just wondering, is somebody trying to ask a question? The volume's a bit low. Okay, don't think it's a question. I think it might have just been a mic. But please do pause, just unmute yourself and ask questions if you have them. So we got to the landscape units, and then we also have the HRUs. So to get the HRUs, those hydrological response units, that's a process of merging, that's a joining of a few different things. So that's soils, land cover, land use, and then optionally slope, and optionally these landscape units, uplands and floodplains. So in this example, the data was pre-prepared, but you would input it as a raster file. You would make your own. So we'll have to come up, I've already done this, but we can, for the uMngeni water catchments, but we can relook if there's any changes that need to be made. But in this example, there's a soils input. So this is a soils map that they have. So it's, in this case, it's really broad soils types for this example. So there's only 2 soil types. And this pink one, VRE, I guess it's vertic soils, just covers a small area down at the bottom here. And then the rest is this blue type that they've coded. And then for land use, land cover, there is 3 types that they prepared for the example. These are agriculture, pasture, so I guess that's cropland, pasture, and forest. And the forest is in very small patches. And then we also input a slope differentiation, under 10% and over 10%. So it looks at the DEM that we've input, and it maps out what areas are under or over 10%. So you could choose different thresholds. You could make more than 2, etc. But the more you break things up, the more HRUs you're going to have. So you always have to ask yourself, like, is it worth? Does it help me a lot to break things up in this way? Because every time you add more classes, you'll have more HRUs, and there's more calculation time for the model. But you also want to break it up into classes that are what you want to be looking at. You want to differentiate between things that you are going to apply different, like, fertilizers to, or areas where you think there's different water quality issues, or areas that you think are really, really different to one another for anything that's going to influence hydrology or water quality. So definitely things, you differentiate between forests and grasslands, obviously, but like different subcrop types, we may want to differentiate and make HRUs. So the slope classes, sometimes I don't use them myself because this soils map is super broad. As I said before, it's only got these 2 classes. So then you probably would want to differentiate the slope classes. But if your soil map is already based on slope, which some of our soil maps are, I wouldn't then split it up by slope as well, because the soil units are already going to differentiate slope. And also people tend to do different land uses on different slopes. So you tend not to have agriculture on super steep slopes. So sometimes the land use follows the slope as well. So you don't need to add the slope separately in those cases. So then all of those got overlaid on each other, and it made these full HRU units. And each one of these units has a subcatchment, a land cover, and soil and slope combination, and a landscape unit combination. Is it upland or floodplain? Is it agriculture, pasture, forest? Is it soil type, LX or VR in this case? And is it under 10 or over 10% slope? And what that gave us was this full HRUs, and there are many, many, many of them. I think there were over 700 or something. And then what we did was we did some merging. And so you can see there are these dark green ones are ones that we decided to not represent in our model calculations because they make up a small portion of the area. So in comparison to other ones. And some of them look bigger than you think they might, but the thing is that some of these HRUs, it's not a contiguous thing. So like if I select one of these, you see I select here, this is one HRU, even though the area is not contiguous, but all of this land is in the same subcatchment, the same landscape unit, the same land cover, the same soil. So that's why, like, this one, that's this piece that got lumped out, it looks a bit big, but compared to the other one, like compared to the other HRUs, even though some of these are tiny, these look tiny, they're part of a larger class that's not contiguous, that makes up a good proportion of this subcatchment 8 for example. I hope that's making sense to people. So those are the steps that we went through, delineating watersheds and creating HRUs. And so our next step in the model, in setting up the model and running it, is going to be assigning the climate data and then assigning the parameters to our HRUs, to our land covers and our soils and our aquifers. And then the model will do the calculations and the channels, actually. So before we move on to the SWAT editor part, where we're going to click on here and it takes us over to that other software, does anybody have questions about this part or any technical issues in getting to this stage? Everybody all right with that part? I see a thumbs up. Okay, great, great. All right. So then if once you've gotten to this stage, you have your HRUs. If you made different decisions than I did along the way, they might look slightly different. Like I put this little point over here, so your subcatchments might be a bit different than mine if you put other points in and so on. So then your next step where you would go edit inputs and run SWAT plus. You click on this guy. And because we opened SWAT plus editor last week, and started a project, it says, has my watershed changed? Because I'm coming to it from this window. So it's asking, yeah, did you run steps 1 or 2? That's this delineate watershed HRUs. Have I redone that since I last opened my project? Because these two projects are linked, the QGIS project and the SWAT editor project. So it's saying, has I changed anything? Because what I could do, I could go back in and redelineate my watersheds and my HRUs if I realized I wanted to change something, and then come over here. I could save a whole new project with a new name if I was doing that, or if I knew that what I'd done before, I don't want to keep it, I could redelineate over here and then come through. So if I had changed things, I would say, yes, import the new watershed, but we haven't changed anything, or I haven't changed anything. So I'd say no, continue to editor. So it pulls everything, so it doesn't bother talking back. It had saved all this information from before, and it doesn't now go back to the GIS because I said I haven't changed anything. And so let's just take a time. I think I rushed through a little bit. I went straight to inputting the weather data as the tutorial suggests, but we didn't pause to sort of look at this interface for a minute. So let's do that now. So you have this interface here for SWAT plus editor, and this is the place where all the data, the parameter values that get assigned to every land cover type, the aquifers and the soils, and so forth get stored, and where the calculation code will be run from here. And then there's ways of looking at the outputs that actually happen back in QGIS so that you could look at them spatially if you want to. So this landing page gives you an overview of your project. So it has the name of the project. It shows you where it is in your directory. It shows you when you last saved it, which was nice, and that's our last session. It's set up with a simulation period. This is the default. We'll change this. Or this might have been drawn from the weather data, I'm not sure. It gives you the total area of your catchment, and it gives you an overview of the different objects or like units in the model. I want to make it bigger for us. Okay. So it gives you this nice overview. It has how much agriculture, how much forest, how much pasture in our catchment area. There's 158 HRUs after I did those lumping steps and merging short channels and whatnot. There are 27 channel units, 19 aquifers, and then there are these landscape units, which that's the upland and the floodplain. And so there's 2 for each channel unit. So if there's 27 channels, there's going to be 54. And then these routing units are essentially the same as the landscape units. They might be slightly different if you had reservoirs. So a routing unit is essentially the same as a landscape unit. All the HRUs in it will get summed up like the runoff from all the HRUs in a unit, will get summed up and then routed to the next one down. So from the upslope area to the floodplain area and then to the stream. The routing units the landscape units just include HRUs. The routing units could include reservoirs or ponds or wetlands instead, which are not considered the same way as HRUs. But you generally, we'll get into that if we need to, but most of the time it is the same thing. But you could choose to lump a specific water body in, and then just for naming, they would call it a routing unit because it's routed together. And then there are point sources or inlets, and those are the heads and tails of all the channel units, as well as the internal points. So it creates I turned that off. Can I go back? Okay. It's hard to go back to the GIS without closing this completely, but it creates a point source node for every stream and channel unit that you can use to have a point source input if you wanted to. Otherwise, it has 0 point source, but the node is there, so you could add data as a point source input if you wanted to. So then the next step, so you can, down here, you can close, you can re-import from GIS. So that would be what we just did, bringing all the data in again. You can change the project name, and then this toolbox is for calibration stuff. So we'll come to it later. This one, this guy, you can download this image. You can view this data as a table. You can view in full screen. Okay, that's what that is. Yeah, and if you hover over it, so that's quite nice. You can get information there. To go through these menus, there's opening another project, create a new project, recent projects, where project setup and information is here. And then the next bit is editing SWAT inputs, is this pencil here down the side. Then there's running SWAT plus, that's going to be running the model, and then SWAT output check. So we're going to go through these steps down the left. They've ordered them as you would. So you would come in here, your project setup information. The next thing we're going to do is edit SWAT plus inputs. So when you click on edit SWAT plus inputs, it orders things also in the way you would, well, okay, some of it's not in the order I would address it. Is it alphabetized? No, it's not alphabetized. Okay. Yeah, I guess this is the way you would go through things to some degree. But we'll look through these. You would go through all of these before you finish up and run. But the first one you would do is climate inputs. And it gives, what's nice is it even tells you here too, that there's this book icon that takes you to that website I showed you with the inputs and the outputs on every page with a link to the relevant page for what we're working on. So, oh yeah, any SWOT. So the SWOT inputs, we're editing them all here in the SWOT plus editor, but in the back end, it's saving everything, all the information, all the values are getting saved in small text files that when you actually run the model, it looks at the values saved in those text files. So you can actually go and modify those text files if you know how they're structured. But if you don't want to learn how they're structured, you edit them here through this interface. So that's basically what this is telling you. But the thing to know is if you do your own editing in the back end, and then you also have this open, this will overwrite what editing you do in the back end. So you have to be careful about that when you tell it to run SWAT. But I don't think that'll be an issue for most of it. I do some editing in the back end, and then I have to be careful about how I use this program, but I doubt you'll run into that. So so under the climate, there's the weather stations and the weather generator. And what I did mention about the weather generator, the weather generator is used when you don't have station data and when you need to fill in a lot of gaps in your station data. And so we input this last time. I might skip going through the inputting step, but I'll show you what the weather generator is. It's essentially just statistics for a station point, but it's statistics on like the max temperature and the min temperature, maxes and mins, standard deviations, average precipitation on a day, standard deviation, the skewness of that distribution for each month of the year. So you could prepare your own weather generator for an area if you had these, and then this is just the average solar radiation on a day, dew point, wind speed, that's humidity, and the max. So these are statistics around, oh yeah, probability that a day is dry, probability a day is wet, how many precipitation days you usually have in that month. So if you prepared all these statistics for an area, you could make your own weather generator. They also have standard global ones in a gridded format that you can use for SWAT as well. We tend not to use this so much because we're usually inputting our own time series data. But if you didn't have a time series data and you wanted to do something like a climate change scenario where it didn't really matter if it was exactly matching some observed pattern of stream flow, it would make up an imaginary time series of climate that worked. So like the temperature would change in line with the rainfall events, and the humidity and those kinds of things would change in line with the made up rainfall events. And it would make this synthetic or hypothetical time series, and it could be many, many years, and then you could look at that to look at what sort of mean annual rainfall over a long time, or mean annual stream flow, pardon me, for a long period of time, given climate that has that general pattern. So that's the weather generator. It's for making up time series of weather that is reasonable for the area, but it's not exactly what happened. So you don't expect the stream flow to match the actual stream flow, but you expect like the averages and the distribution of values to match the real averages and distributions of values. But it can also get used to fill in gaps if you are inputting weather station data, or you can choose to fill in gaps on your own, but this is a nice way of gap filling for you. So then you do the weather station data. So if you actually have weather station data, you could calculate these statistics for it and make a weather generator file. Then the next step, which I don't think we did last week, is, yeah, we didn't do it last week. So this is where we are in the tutorial, is inputting the weather stations. And so the weather station data has already been prepared for the tutorial. Actually, all the input data has been prepared for the tutorial. And when you're adding things in SWAT Editor, but you have to look down here at the bottom for these buttons. There's import data. So we're going to import our weather station data. I'm just going to show you also the tutorial file in case you're following along to see. Ooh, excuse, my window is jumping around. We are in 6.3.1. We already imported the weather generator data as these two files, a stations file and a monthly values file. Now we're going to import the weather stations data. And we're going to import, we pick it as in this, there's different ways you can format your weather input data. So the tutorials format is this SWAT 2012 format. I think they've made some other format options more recently. So this, it has you navigate to a folder where your weather files are stored. Okay, and then this is the directory to save the output files. So I would leave these as the defaults it's going to make for you. And then it will give you a window where we input them. Okay, so it just asks for the folder where they are. So that means that you have to use the format that they specify. And then when you give it the folder, it will find the files. So that means the files need to have the name that it expects, because we're not giving it the actual files, we're giving it the folder where they're stored. So I'm just going to show you the folder structure quickly, and then the folder and the file structure, and then we'll import it. So if I go to my Windows Explorer and I go to my local disk where in my QSWAT projects folder, and here's I ended up with two subfolders by accident, but like a nested folder, but that's fine. Then the climate data, the climate inputs are in this climate robot folder. So I'm going to direct it to there and it will find the files. But I want to show you what the files actually look like. So if you open that folder, you should have the same one. This was pre-prepared for the example. You have these different files and they're called, so PCP is precip, HMD humidity, SLR is solar radiation, TMP is temperature, WND is wind speed. So you have those, and then you have, because the catchment's called robot, there's ROB PCP, so that's robot precipitation, relative humidity, solar radiation, temp, wind, with the robot in front. So these are text files. If I open this one up, so PCP, this is the precipitation one. What this one has is the information about where the station is. So this is the precipitation station. There's only one of them in this example. So in my presentation, I showed you, I think I had 4 there, 3 weather stations and 1 rainfall gauge. In the tutorial, they just have 1 gauge to keep it simple. Not the best, but it makes it run quicker for the example case. So they just have 1 station. So you would, for another model, you would prepare a file that would have as many stations as you have. This is the name of the station. This name of the station needs to match the file name where the data actually is. So the pcp.txt, it needs to be called this because this is what the model looks for when you tell it these files are in the client, this folder. So I say, look at climate robot, you will find pcp.txt there. So it finds pcp.txt, and then it looks for the station name of the rainfall station. So they just call it robot PCP. So you could give it any station name you wanted. But then whatever station name you give it, there needs to be a file with that same name. So that has the actual data. So this is the file with the locations of all the precipitation stations, their latitude, their longitude, and their elevation. So you would prepare a file like this with all your stations, the latitudes and longitudes of them, and the elevations. And then it would then know that that's where the point is, and then it would look for the data file that has the matching name to the station name. So then that file, this has rainfall for every day. It's a very simple text file format, but it's daily rainfall. You tell it that it's daily. And then this is the day that the data starts, 1990. January 1st, 0101. So it's 1990, 0101. So that's January 1st. It has the start date at the top, and then it just has a sequence of values. So no rain, no rain, no rain. And then down here it starts raining, 2.3 mils, 2.3 mils. So this is the time series of rainfall, daily rainfall days. You would have to tell it if there are gaps, there would be a no data value. I think it's like -99. We'll have to look that up in case, but generally, I try and fill the gaps myself outside of the program, but I'm starting to see because I haven't you could prepare a weather generator, but I often use a nearby station. If you have nearby stations, filling in the rainfall based on the relationship between 2 stations is also a good option. So I tend to do that rather than doing the weather generator option. But if you wanted the weather generator to fill it in, there would be some no data value that instead of a 0 or a rainfall value, it would have like, I think it's often -99, but we can look at that. So then you have your rainfall time series for this station. So it has the same thing for humidity and temperature and solar radiation. The temperature one has minimum and maximum temperature, so it's a bit different format. So the temp.txt file has that's what they've named the station, robot temp, and there's a file with that same name, and this is the latitude and longitude and the elevation. So you can see it's actually at the same location as the precip one in their example. And there's the temperature. So now this file has the same start date, and then it's daily temperature, max and min. So 25 was the max for the day, 9 was the min for the day, comma separated values in a text file. It goes down out to 1 decimal place. So there's all the data there. So when you set up your own model, you need to prepare this data in this folder. I'll be doing that for the uMngeni water model, and I'll show you how that looks. And then I've written some code that prepares these files from the data formats that we're going to get the data in. But I wanted to show you what this formatting looks like, because this will need to be prepared. And if further down the line somebody else wants to modify it, you'll have access to the codes to help you format everything in this way. But this is the format that the climate data is in. So when you import your weather stations, it's asking you about the format. So that format I just showed you, where you have these files that are named ptp.txt, relative humidity, RH, relative humidity, solar radiation temperature, wind. Yeah, they have you can download a sample format and read instructions on formatting them in that format. So that's the SWAT Plus Global Data Websites format. There's a new format that they've made, which is the tutorial. Okay, so there's this file. So that joins the locations and the text files into the location and the data into one in these .cli files. And there's a way, instructions for importing that. The tutorial has us using this format, and this is the format I've used before, and I've already made the data from uMngeni water in this format. But using the instructions, we could, I'll just open these so you can have a look at what this looks like. We could switch over to this if we wanted to. I'll explore it more, but let's just see. It's nice to jump over to the documentation. That's the weather generated data, observed weather data. Okay, this takes us to the SWAT. This goes into that folder structure I just showed you, or the file with the location information, station name, latitude, longitude. And then, okay, the SWAT Plus has, okay. So that .cli file gives you the file names of the station data. And does it say where the elevation is? Okay, yeah. So then it has a file structure where there is a day of year and a year instead of that date at the top. Okay, the number of years, number of time steps, lat, long, and elevation is in that text file. So either one works. It all has the same amount of information. This file would contain a list of the station names, and then the actual station files themselves would have the lat, long, and elevation. And then the way the time series, it doesn't have the date at the top, it has the year and then the day of year. So it'd be like one until 365 in the file. So these are just two different options for formatting the input files. This file almost looks more messy to me because you have this section here at the top that's a different format from the section below. But all formats can be a bit tricky to get into if they're not the ones you already work in. So those are the two weather station input formats in, but let's go back to the tutorial one. SWAT 2012 is formatted that way. But it's the same theory as you can see. So then you have to tell it where is the weather files directory. So we're going to go to this folder here and we would navigate to our climate robot folder. And that's where all the files in there format, the format it wants are in, and you select folder. And then you have the directory to save your SWAT plus weather files to. And I would leave this as your default. I'll go into this structure soon, but it does some processing. What it's saying here, so you have your directory. This is where the input data for the stations is. So where the weather stations are and the time series data for the weather stations. This output is going to be where it assigns, it's going to assign that data to each HRU. So this folder is going to be where it puts the information about which HRU gets data from which station. And then that linking gets saved here, but you don't need to change. I'd recommend not trying to change this. And we'll go into this scenario's default text in and out folder. Pretty much everything about the back end of the model gets stored in this folder that it makes for you. So I'd leave that as it is, and that's what the tutorial also suggests, but generally just leave this one. And so then you click import data. Import your weather station data. And then it's found the data. It's made this name. So it's got, that's the weather generator. That's the link to that file that was called that in the previous step that we looked at. And then it's found that there's one station for precipitation, one station for temperature, one station for solar radiation. It's pulled the data in. As I mentioned, it's calculating potential evapotranspiration from temperature, solar radiation, relative humidity, and wind speed. The other option is that you could calculate that outside and not give it all of this, give it potential ET yourself. When you do that, it calculates a lot of other things differently within the model, because it's always going to need temperature, actually, because the temperature affects the plant growth part of the model. So you will always need precipitation and temperature, and then either you give it these other bits or you calculate potential ET somehow else and put that in yourself. But it's always actually going to need temperature. It will calculate the plant water use a bit differently if it uses this version than this version. And this one is recommended generally, but sometimes this makes sense to do. But now that we have a lot of satellite remote sensing based products that can give and global weather models that use station data and stuff to reanalyze and make these other weather products, it does make sense to find and put these in individually anyway. Again, if you need help on things, you can always click this help thing and it'll take you over to the website that explains all the parts. So now we've put in our stations. If you were to click on it, I have to double click. Maybe if I edit it. Oops. No, okay. That's the weather station. Okay, go back. Okay. Okay, yeah, sorry, you don't click on this. Okay, if I click on that, it wants to open the text file. Sorry. I just want to show you how to do everything. But if you click on this guy, this is editing. So if you click on this, you could change things. So you could change the latitude and the longitude. This is for the weather generator, but this is the file. It's got the precipitation and it's saying simulated, and it's not simulated, it's using the observed file name. And it shows you them again here. If it managed to get the wrong one somehow, you could navigate. If it found other ones, you could add them there. So I'm gonna just go back because we're not changing anything. So then before I move on, is there any questions on inputting the climate data and what it's actually doing with that data to assign it? Is that going okay? If people are following along in their own computers, are you keeping up? Nintendo, yes.
Yes, Dr. Chula, I just wanted to find out if what is actually going on when you assign the climate data. So are you assigning the climate data to each subcatchment, and all HRUs within the subcatchment will receive the same climate data?
Yeah, so it's similar to that. And for people who have used ACRU before, for example, ACRU would assign climate data by subcatchment, but SWAT does it slightly differently. What it uses the location of the climate station. So when this precip.txt has the information about the precipitation stations. This one has this latitude and this longitude that gives the location spatially of this station. In this example, there's only one, but if you had many of them, what it would do is look at where it assigns it to each HRU rather than each subcatchment. So let me just pull this up again. So it's going to apply it to each HRU. So we have our map of HRUs, and it's going to see for each HRU which station is closest to it. So I drew these lines just showing like this area is all closest to this station. So all the HRUs there would be assigned the data from this station. And all the areas in this box, regardless, so you can see it crosses different subcatchments. So what it means, the reason they do that is so that you can input your stations wherever they actually are, and it will assign each HRU to the closest one. They used to actually do it by subcatchment, and now it's actually by HRU. So it does mean that like these HRUs on this side of this subcatchment will be assigned to this station, while these HRUs on the other side are assigned to this station. So this does have some implications. Actually, if you think it's more realistic, like if you think these areas should not be assigned to this one, you might want to make an imaginary station in another point that will make sure that these HRUs get the weather data you're hoping they're going to get. Because what it is going to do is assign them based on the closest station. Does that make sense?
Yes, it does. But I also wanted to find out, just from your explanation. So you actually need more stations to account for maybe climate variability or your rainfall variability per HRU, because I assume that if you have maybe one station representing maybe hundreds HRUs, you might find out that some processes may not be realistically accounted for.
Yeah, exactly. Exactly. So that's always the difficulty because we never have as much rainfall data as we want, unfortunately. And like as a country, we lose stations too. There's stations that aren't getting maintained. And so the more rainfall stations, the better to get the spatial distribution that's actually happening. And sometimes you have rainstorms that are quite localized. I'm sure you've seen it where it like rains on one side of the mountain and it's not raining on the other side of the mountain, or those kinds of things. So the more stations, the better. There also are now there's gridded rainfall products, that rainfall data products that get made. So they'll combine station data and satellite estimates. And we're probably actually going to use one of those. It's HydroNet, and that combines station data and satellites, because the first prize is to have a really good station network where you have stations at high elevations and low elevations, and the north side and the south side of the mountain, and all of that. But we generally don't have that, unfortunately. So like the next best thing has been to mix satellite products and models and station data together to try and fill in the spatial gaps. Now, this structure is designed for station data inputs, but if you have a grid input, like a raster data of rainfall, where every grid cell has a rainfall value for every day, which is what what the satellite products and some of these combined products would be, then you pretend that the center of every grid cell is a station. And I'll show you that at a later point. But I think the big message here too is that for every point you give SWAT, it's going to assign the rainfall data and the other temperature variables to each HRU is going to get the rainfall data from the closest station point that you input into the model. I saw somebody else might have also had a question. Suisile, did you have a question? I saw you unmuted for a sec.
Sorry, Julie, it was a mic. It wasn't a question, thanks.
Okay. Tando, did I answer that? Cool. See a thumbs up. All right. Yeah, so one would need to then prepare data for all the points you want to enter for. And they are stations. It was designed for stations, but now we might be using other data inputs. So we would input for other points, pretending that they are stations, if it's a satellite data product, for example. But essentially, it is designed for every point where you input a data time series, it will assign each HRU the data from the closest one. The tutorial just has one station for the whole area, which is not what you would actually do. It's just trying to keep things simple for the sake of going through the software. But we'll show you the inputs. This is just to make it run really quickly so you can do the tutorial without waiting for a long time for the model to actually run. And get a feel for the file formats and stuff. So that's the weather input part. And it's a very important part of preparing any model though, because if your rainfall input data is way off, you can do whatever else you like. Your model's never going to be very good, unfortunately. Well, it'll have inaccuracies that are related to the rainfall inaccuracies, and you won't be able to fix those. So if your rainfall data is not great and you know it, then you just have to be prepared that your outputs are going to be relatively inaccurate. That they will tell you something, but you can't expect them to match the observed stream flow very well. And like if you know that it rains, like the peak rainfalls are higher in some parts of your catchment than your stations are able to capture, then you'll just have to know that the stream flow at those peaks you're never going to get your model to really match exactly what's happening. But maybe it can tell you, the model may still be able to tell you which part of the catchment has more nitrogen runoff slightly, but it will still be a bit off because it's going to miss those peak flows in that one part of the catchment. So you just have to be aware that if your rainfall data has a lot of problems with it, you're going to struggle to get a model that matches the observed, and you'll have to be quite careful about how you use the outputs. Unfortunately, that's like always the case. We always have limitations with the rainfall data, but we're having better and better options with these combined products. But ideally, what we'd want is a really good station network as well. So this is a really important part of the process. So the next section, if we're just going to move down through these sections and look at what they are, and then we'll do a model run and look at the output. So down here, you can, on these windows, as we go through the various places to edit the model inputs, we just did import data. You could delete all and re-import and start again. Creating a record, I think, is adding a new one of these rather than importing. Let me just click on it and check what it is. Create record. Oh, okay. So it's a new, it's a new station. Creating a weather station manually. You'll need to edit. Okay. So this would be a way to put together a new station instead of preparing it. I'm preparing all the files separately and then telling it where the folder is. I'm just going to go back. We'll leave that. So we're done with this part, this weather stations part. let's go to connections and have a look at what's there. So this menu expands and contracts the way that a folder like Microsoft, like your desktop explorer or your file explorer would be. So you can expand and contract. And then, so if you expand the connections menu, you can see channels. This shows you all your channels, their location, the area that's feeding to them. And then it has these initial values where it gives you the name of the file where the initial values for the channels are stored, the initial nutrient values, the file where those are stored. So these are file names, and then the weather station that so channels have weather stations applied to them as well. It's also the closest one because the channels have evaporation off of them. So this shows you the linkages. So when we did that import process, it looked at spatially the lat long of the channel versus the lat long of the station. In this case, we only have one station, but if you had multiple stations, you would see which station gets applied, like gets which weather data. And then it has outflow, and then this one doesn't have outflow because this is going to be an end. This would be the end. So I guess channel 52 is going to be our final outflow from our catchment because you can see it has a 0 there. To see what's in these, so like I said, these are file names for the initial channel data. So it needs a starting point. How much water is in the channel on day 1? And that's here. And it has no organic materials or pesticides or pathogens or salts in it. For example, if I click on edit, this is the initial state of it. Okay, this is not how much water it has in it, apologies. It's just how much of these water chemicals it has in, if we wanted to include that. And then the initial hydrology is here. Yeah, okay. And then nutrients. Okay, so this is just for, this initial is just for organic material, pesticides, pathogens, and salts. These files are the hydrology files for the channel. This is the order of the channel. Is it first order channel, etc. So this data is similar to what you saw in the attribute table in your GIS. But these are the values the model is going to use for the channel when it's doing calculations. So it has a width and a depth and a slope and a length, a Manning's N roughness. So that's going to determine how quickly water flows through the channel as well. So is the slope. This is an erodibility factor. So that's going to determine how much sediment gets mobilized. A cover factor. Sinuosity. So a lot of these, and then like the clay proportion, carbon, bank full flow, the nitrogen concentration, the phosphorus concentration on day 1 of the model run. It'll then model the nitrogen concentration and the phosphorus concentration going forward. If you happen to know what it is on day 1, you could put that in. But otherwise, you just run it with 0 from day 1 and you let the model run for a little bit. And then you only start looking at the outputs after it's run for like a year or something so that these concentrations become realistic. That's why I mentioned it before, you often do a bit of a warm up for your model because you don't really know what the conditions are on day 1 of your run, and the model needs to start with something. So you run it for a year, sometimes 3 years, and then you only start looking at the model outputs after it's done 3 years of run so that these initial values start becoming realistic because it's had some runoff from the landscape. It's had some groundwater coming out. It's had some accumulation of stuff in the soil according to the model. So these are all the values that are assigned, like the parameter values for the channels. If you need to see, so this, if we go to the help, for example, if I click on here, it's gonna tell you what all these abbreviations mean. So WD, channel width, DP, channel depth, SLP, channel slope. So it estimates all of these based on the catchment area feeding it. And then there's some assumptions about how catchment area relates to channel width that are in the theory documentation. But this just tells you what the parameters in this table mean and what their units are. So for any of the inputs that we're looking at, you can always just click on that and it'll take you to the website that tells you what these are. So if you wanted to change them, like let's say you know that this channel 2, you'd go to your GIS and look at which one this is. And you could say, oh gosh, I want to change, it's much rougher than the other ones. We're not going to play too much with this because it doesn't, this one, the channel parameters have a bigger effect when you're looking at like sub-daily flood peaks, but we're looking at a daily time step here. But you could come in and manually change these values, the width and the depth and the roughness, if you knew that these were off from what's actually there. The clay percent, sediment size. Okay, this is nice because it gives you these descriptions. And these, okay, this is also in the bank as well. Ah, sorry. Okay. Okay, sorry, I misspoke about what I got confused. I thought these N concentrations and P concentrations were the day 1 concentrations, but these are actually the concentrations in the bed and bank material. So it actually says that here. So it's in the bank, so that's when the bank starts eroding, how much nitrogen will end up and phosphorus will end up coming into the water from the channel bank if the bank starts eroding. The day 1 stuff is actually here. And if I go, so this is nutrients for the channel. So if you go in there, the parameters would, so there's a bunch of parameters here. Biomass, oxidation rates, settling rate, channel organic P. Okay, yeah. So that's going to be channel organic nitrogen, phosphorus. Okay, so it doesn't have a non, definitely has a day 1 for the soils. It has an organic one. It doesn't have the I don't see the non-organic day 1 factor. Just has fraction of biomass. So as you can see, there's lots of parameters for all of these units. And these defaults, the model will, when you start the model, it will have all these default values in there. As you've seen, like we didn't put any of these in. It came with the default value. So these are the default value. This is a recommended range. And we have to decide if we want to change these for our model as a whole or for individual channels. So if you on the book, so one would see the same thing here. Does this take you to the theory? No. So to work out what these values should be in different cases. So I talked a bit about this when we were talking about water quality. There's like die-off rates for the channels for if you're doing bacteria. There's rates of settling. There's rates that nitrogen and phosphorus and stuff change form depending on temperature, etc. So if I click on this, is it gonna, okay, it doesn't tell you, it just tells you what it is. But to sort of look at what some of these values what you might want to pick for them, you would go to your theoretical documentation, which is down here on the left. And then you do main channel. So in this example, main channel processes, in-stream nutrient processes. If I was looking at the nitrogen one, I could go to nitrogen cycle. And then you can go through and you'll see how each of those parameters is getting used. And it often has some, doesn't have suggestions for these ones, but it tells you how it's getting used. So you would understand what you might want to change and why. And then this links how this is linked to other processes in the model. Just want to channels. There are some parameters where it gives you, so some of these parameters, when I set up the model for the uMngeni water catchments, some of them there are suggestions in the SWAT theory documentation for different kinds of settings. Some of them I've gone to other literature to find them. And we'll go through that. And some of them I've left at the SWAT defaults, and then you look at how well the model performs and you adjust them. So these are some of the parameters we have for channels in the model. So there's this initial state in terms of organic material, pesticides, pathogens, salts. There's the properties that are related to hydrology and sediment. So that's size and erodibility and sediment. And then, yeah, this is, sorry, the concentrations in the banks. And then there are the parameters about how nutrients move. And I believe these are the initial ones, but it said only initial organic. So I guess the other inorganic comes in over time. I guess it'll assume starting point of 0. And then all these parameters are about how the nutrients get processed within the channel. So those are various parameters around channels. HRUs, this is going to be all, this is data for all, each HRU has the area, the lat long, the weather station that's been assigned to it based on closest. And then there's a file. So when these names are blue, it means there's a file, or like there's a separate data file that would be about this that has, so there's a bunch of data about the topography that's in this file. So if you wanted to edit it in the back end, you would go to where that file is as a text file and you could edit it there, but you can also edit it in this interface. But it's just telling you also what the file name is in case you go in the back end to edit it. For this, so for HRU1, there's a file called topography HRU001 that has the information, and a hydrology one. So, but you can also edit it here with this edit button. A lot of this is already this is all calculated by SWAT already, but if you wanted to change what it's done, you can go in and change it here. So if I click edit on this for just for HRU1, you can see what's inside. So it has topography properties. So it tells you where the file is, database. You can browse table. So let's see what's in topography for HRU1, for example. It has slope length. Okay, this is showing it for all of it. Slope length, latitude length, so that there's like a flow length across it, but they match the slope length in this case. Distance to the channel, I believe, but these are all the same. So we could, and then there's something about deposition and type. That's another page. Oh, okay, yeah, because there's so many HRUs, it's just showing them on different pages. So if I want to look at if I click on the help, I can look at what all of these are, pointed to the topography file. And if I want to see what's in the topo file, it's you keep clicking until you get to a table of the neck. So let's just check. Oh, distance channel is currently not used. Haha. That's why it was all the same values. And then deposition is a deposition coefficient. Okay. So every HRU has all of these properties. Same with routing units. This is going to contain which HRUs are inside which routing units and how they are connected. So it has all these HRUs and it has the fraction of it has which routing unit is this HRU in. So I said the HRUs and the routing units and the landscape units are the same thing in this case. So you can, this is like the upland and the floodplain. So HRU 1, 2, and 3, and 4 are all within routing unit or landscape unit 22. And you can see that in our GIS when we were looking at the attributes tables for each HRU, you could see which landscape unit, which subcatchment, etc. they're in. If I click on this, it's going to tell me the area, the elevation, the field properties. Yeah, and it tells you the outflow. It's going to outflow into channel 2. Okay, so this is an upland. This is 22. And then 21 is going to be, this must be an upland one. I was hoping it was going to tell us that here. Can you see it? Browse table. Because we're looking at routing unit 22. This is telling me the HRUs. Okay. And let's look at this one. Field, browse table, floodplain. Okay. That's how we know it's the floodplain one. Floodplain 22. Okay. So this routing unit is associated with the floodplain one. But it's not. This one is a, pardon me, I thought it was going to tell me here which kind it is. Maybe it's up here, but it is, I can tell already that this one is an upland one. And the reason I can tell that is because it's routing some surface flow onto another routing unit. And if we were in a floodplain one, it would all be going to the channel. So what this table is telling us for the routing unit is that from this routing unit, the way that it's set up right now, this is surface runoff. Surface runoff, it's sending 84% of it to the channel, and it's sending 16% of it to routing unit 21. So from that, I know that routing unit 21 is the floodplain one, and then this routing unit 22 must be the upslope one. I thought it told me that somewhere else in the table, but I was wrong, sorry. But then this is the lateral flow. See how it says lat there? 100% of the lateral flow, that's the subsurface flow, from this routing unit is going to go into the floodplain one, this routing unit 21. And then the aquifer outflow, the groundwater outflow, all of it's going to go into the floodplain one. So all of the aquifer outflow from 22 is going to flow into aquifer 12. And so this number is different is because there's only one upland and one floodplain aquifer for the whole subcatchment. Whereas there's multiple landscape units per channel within the subcatchment. So this all goes back to those structure diagrams I've been showing you the other times. So if I show you this in the help, pointing units, topography file to the field file. Okay, that's not. is helpful. I thought it was going to show us about the outflow table. Apologies. But if I wanted to change this these fractions, I could change these fractions if I thought that what this is telling you is that some of the way it's set up, some of the surface runoff is going to make it all the way to the channel directly, whereas a portion is going to get caught by the floodplain area. And the reason they do this way as a default with like 84 and 16%, we can check a few others and see what the fractions are, but it usually is around, the default's usually around like 80-20 or 75-25 or 8. And I think there's a way that they estimate it based on the size of the channel and the size of the landscape. But the reason for this division between some of the surface runoff getting routed onto the floodplain where it can infiltrate and some of it just going directly to the channel is because in a very high flow event, the floodplain area is actually going to be saturated. So the water is just going to run straight over into the channel anyway. There's no chance for it to infiltrate or stop. And also if it ends up in like rills or other channelized flow in the landscape, it will run straight over into the stream without having a chance to infiltrate. But if you think that that doesn't happen very often, and actually it does generally, you want the model to calculate all of it having the potential to infiltrate on the surface all of the time, you could change this to 100% and change this to 0%. And so you would do that, you would edit this, and that's from, surface fraction, surface flow. So these are the types of flow connections. This is a surface flow connection, a total flow, a recharge, a lateral, and a tile drainage, which we haven't gotten into. So that's a connection, but this is a surface. We're not going to change that. Ooh, don't freeze. Oh, sorry, my computer's freezing a little bit. Oh dear. While it's trying to connect, go back. Okay, there we go. So we could change that fraction and we need to make sure that it ends up, this is a connection to the channel. You could connect it to a reservoir recall. I'm not sure what recall is. I think that's leaving the model. There's different connection elements, but you wouldn't change these parts, but it's just saying it's connecting to a channel, it's connecting to channel number 2, it's a surface flow, and that's the fraction. But I'm not going to change it, I'm going to leave it. Let's just look at another. So if I go back, I'm not going to change anything. We were looking at these routing elements. So we were looking at RU22. If I look at RU21, this one, as I said, is the floodplain one. So all the flow total, so it doesn't break it up into surface, lateral, or groundwater flow. All of the flow out of this routing unit, so all of the HRUs and the aquifer in this routing unit are going to go to the channel. And then there is an aquifer recharge portion that goes into that aquifer, and this is the floodplain aquifer. But the outflow, the floodplain aquifer, is going to go into the channel. That's what this total outflow means, and this is recharge. So that's 21. So we could see that 22 flowed into 21. I had thought for some reason it was going to tell you more about that this was a floodplain here in this table. But it does tell you, and you could go back to your GIS table and see that. So that's the routing element. So when we're into connections, this is really these flow connections that I showed you in diagram form before. So you can go in and change each one of these. You can also change them as a group. But that's actually easier to do with coding through the back end, actually, which is if people really need to do that, I can show them how to do that, and I will be doing it using coding. Otherwise, you have to click through lots of menus if you've got a complicated model. This is showing you all the different aquifer units and then the properties that they have. So these are aquifer unit 11. So if you went back to your GIS and you clicked on your landscape unit, your final landscape units, you would get these numbers. And if I click on this one, you can see some of the properties that it has and how it outflow and what its connections are. It's going to outflow to channel number 21 and potentially to that deeper aquifer, and in this case, number 7. And it has all of these, some of these are initial properties. Some of these are properties like the base flow rate, the recession curve shape for the groundwater outflow, how nitrogen moves through, like how nitrates degrade. So you can see all the different properties that one has to assign for each aquifer. And there's initial properties like the initial flow out on day 1 in millimeters. There's the initial depth. And, oh, sorry, that's the initial depth. Depth to the water table. And when it says depth mid-slope surface, it's imagining the groundwater table has a slope from, you know, the highland to the lowland. And so what's the water table depth at the midpoint? And there it has 3 meters. So it's not assuming that the water table depth would be the same everywhere in the subcatchment, but that's the depth from the ground around the midpoint of the slope. And then that's the depth to the bottom of the aquifer. So if there's another layer, so they're saying the total depth to some other confining layer, some other rock layer that differentiates to the deep aquifer is 10 meters. And then the water table is sitting 3 meters below the ground on day 1 of the run. And then it has the nitrate concentration, phosphorus, all of these base flow rate when the entire area is contributing to base flow. So that means when the aquifer is full. And then as the aquifer dries out, what is the shape? This is a factor that controls the shape of the outflow recession as the water table drops. And then you can have a threshold depth of water in the aquifer before base flow stops. Oh, apologies. Sorry, that's the wrong parameter. I meant that's for revap. Okay, so that's the depth of water required for actually for the roots to take some water from the aquifer when the soil moisture is low. Apologies. That was the water table depth where outflow stops is this one, flow min. And the water table depth, okay, that allows the plants to access it is here. Revap min, yeah, okay. That's where it starts, and that's where it stops for plants to access it. And that's how nitrogen degrades. And this has to do with the porosity of the aquifer. So when we would need to assign these properties to all the aquifer units in the model. And this shows how they're linked to the channels. So this is this connection section still. So as you can see, there are lots of parameters in this model, lots of values assigned to all the units. And then there are default ones that SWAT has already assigned. All these parameters, I didn't put these values in. Any model you set up, the default values will automatically be in there. And you have to look at them and decide if they need changing. So even if we set up a fresh model, not this tutorial, all of these values, it would assign all these values to the aquifers. Those are the default values, and to the channels and to the HRUs. And I'll show you the land cover ones after we're going to take a short break now. We don't have reservoirs in this particular model or point sources. I'll just show you this groundwater flow. So we'll skip this one for now. But and go into this when we go into how we set up reservoirs for the uMngeni water ones. Same with point sources, but it would have what's getting input for each point source. And then groundwater flow. Okay. This is when you have a different, the different groundwater model than the one we're using. Okay. I forgot, pardon me. So we'll skip that one. So we actually have gone through all the bits that we're going to go through before we get into particular. We're not going to go through all of these. We're going to go through the soils and the vegetation ones, because some of these don't apply to what we're doing in the tutorial. So I think let's take a break. But before we take a break, does anybody have questions on what we've just looked at in terms of, you have all these parameters for the channels and the HRUs and how the routing units are linked and how the aquifers are linked. And that all speaks to these HRUs we created and landscape units and aquifers that we created in our GIS. Don't worry, we'll see all of this a few times. So it should become clearer and clearer every time we go through it. All right. I see stony silence. I might have lost everyone. Let's take a break until we've gone a bit past half past. So it's 10:40 now. Let's take a 15-minute break. Let's come back at 5 to, let's take a 15 break and come back at 5 to 11. Is that all right? 10:55. All right. See some thumbs up. All right, so let's come back at 10:55. I'm going to pause the recording and stop sharing my screen, and then I'll talk to you in 15 minutes. Hi, everyone. Thanks. I see a thumbs up. I think people are coming back. I'm gonna start sharing my screen again. And full screen. So I hope people can see my screen. And I will start the recording again. So welcome back. I'm not sure if everyone has joined again, but I'll recap a little bit and hopefully everyone will have joined before I say anything too new. So what we're doing now is going through the various pieces of the model that you can see in the SWAT Plus editor software. And before we run the model, and we entered the climate data, which is something you have to enter, and then the rest of the parameters will have default values in them for now that one could change. And then some of these values have also come from the calculations that the software did for us in the GIS. So all the topographical stuff like areas and slopes and lengths and connections between one unit and another, all of that was determined by the topography in our GIS part. It doesn't, when you have the SWAT Plus editor open, you might have tried this already. I've noticed this on my computer. I can't go and play with the GIS separately. So you see my spinning wheel here instead of a cursor when I try and go back to the GIS window, the QGIS. So it doesn't want me to go back there separately. The reason why I can't edit this while I have the SWAT Plus editor open is because these things talk to each other. So if I change something here, it's speaking to attribute tables and things that have come from the GIS. So it doesn't want me to, it'll mess up the linkages between them. So I can't, unless I close this and save everything as it is, I cannot play with the GIS at the same time. I find it's a bit frustrating sometimes because you want to go to the GIS and see which unit is which one. But I see why for software reasons you can't, because they're talking to each other. And unfortunately, they don't have like a map interface that's separate and stable in this program that allows you to sort of see which one is this one. So that is a bit of a frustration, but the fact that all the things it does for you in the GIS separately and then imports for you and so it's from a software design point of view, they had to come to a balance, and that's how they've worked it out here. So if I wanted to, I did find while we were on the break, I found out where some of the things were. I thought they were in the connections section, but there is this regions section that I actually forgot about. So our connections section has channels and HRUs and routing units, which are the same, essentially the same as our landscape units, that upland and lowland for every associated with every channel within subcatchments. And then aquifers are also in subcatchments, but there's the upslope area aquifer and the lowland area aquifer for every subcatchment. So the numbering convention for the aquifers, so like I'm pretty sure, yeah, this will be subcatchment 1. Upland aquifer is aquifer 1, lowland aquifer is aquifer 2. Let me just double check that. It might be the other. You can check it. Okay. So sorry, I got that the wrong way around. Forget about that. Aquifer 1 is the lowland aquifer, and aquifer 2 is the upland aquifer. So it flows from 2 to 1, from high number to low number. And so this is within subcatchment 1. this is the upland aquifer is number 2. And then it flows into, you see the outflow goes into subcatchment aquifer, lowland aquifer, aquifer 1, 1. So if we go back to our overall table for our aquifers, you see there's subcatchment 1, upland and lowland, so 2 to 1, subcatchment 2, upland is number 2, it flows into number 1, which is lowland, and you can check it by, like if I go to 2, 2, this should be subcatchment 2, upland, and it should flow into 2, 1, and it's flowing into 2, 1. And all of its outflow from this aquifer, 100% of it is going into aquifer 2, 1. And these are the properties of the aquifer you can change. And the area, and this is the latitude and longitude, the middle, the elevation, etc. So these are all the things in the connection section. I'll come back to the basin one, but the next one down is regions. And this contains these routing units and how many HRUs are in them. And if you click on elements, it shows you which HRUs are in which, oops. Okay, these are all the HRUs, but it shows which routing unit they are in. So we saw that before with the other routing units. But it gives you the fraction of the subcatchment, etc., in that table. So a lot of these things you wouldn't change, but you can see where they are here. You could edit them if you wanted to, but this was all calculated from the GIS. But this is where the list of which HRUs are in this routing unit is here. You can click on each routing unit and see which HRU is in it. And then if you were to click on an HRU, okay, it just shows you the routing unit there. So this is all about the structure. These bits are about the structure of the model, but there are some parameters in there that we might want to change, like properties of the aquifers, properties of the channels. The properties of the HRUs are not really here, except for their topographies and their slope, the things that were calculated topography from the GIS, from the DEM in this section. We'll get down here to the soils and the plants, the vegetation shortly. So that's the connections and the regions, like where all the information about the model structure is. There are some parameters that you can set for the entire catchment at once, and those are here in this basin. So in the US, I think basin gets used as larger than like catchment versus subcatchment. I think basin is like used that way, and then they say subbasins inside. So these parameters, these are code parameters that are like where you choose an option, like a way of calculating things. There are options for different ways of calculating things. And then there are parameter values that are actually like property values. So these are methods in here. So these are different approaches for inputting your potential evapotranspiration, for example. So we're using we're using the Penman-Monteith to calculate it. That's the equation that combines the temperature, the wind speed, relative humidity, wind speed, solar radiation, temperature, to calculate the evaporative demand using that equation. There are other equations you could use, like if you only had temperature, you could use the Hargreaves method. And then the Priestley-Taylor, I think it uses wind speed, but not solar radiation. If you have less data, you can use these other ones, or you can read in your own set of PET values you've calculated separately. For example, so this section is where we change these different method settings. So that was just one example of one method you could change. There's different like specialized things you could choose to represent or not represent. So like cracking soils. If that's a really big issue in your catchment, there's ways of doing it, but the default is to not bother with modeling crack flow in soil. But if we thought that was a big issue, we could turn it on. So this is the place where we do that. I'm not going to go through all of them now. I wanted to get us further along, but I just want to show you what's in this interface. So there's different things you could turn on and off, like a lot of them are off for default, but like tile drainage is a specialized agricultural thing you could use, and so on and so forth. We'll come back to important ones for our catchment later. But this is where these different method options for the entire model get turned on and off in this basin section. Then these are parameters that apply to the entire catchment as a whole. I'm also not going to go through all of them now. We'll come back to particular important ones later. I'm just showing you the structure of this menu for now. But you can go through these at your leisure another time if you'd like. And again, they're described in this help file, but what you really have to do actually is go to the theory on the different calculations that the model is doing, that theory part of the website, to see why these parameters, like where these parameters get used in the calculations. But there's things about water quality as a whole, how phosphorus and nitrogen move in general, and then you'll see there's specific parameters for each HRU. But this basin section are for things that you would set for the entire model, the entire catchment area. This regions one I just showed you, that has which HRUs are in which routing unit or landscape unit. This land use management section has a whole lot of things you can set for different land cover types. But I'm gonna move down and come back up to this one, because I think let's look at the vegetation databases before we look at the management part. That's why I say the ordering of this from top to bottom is not necessarily the order I would put. But I think the reason they've done this is because some people will use the defaults. They won't change the vegetation stuff, but they will change the management. So I think they put the things that people will change more at the top. So we'll come back to management just now. And decision tables have to do with management and reservoir releases that we'll come back to. It's rules for how things can change over time. And calibration, that happens at the end. That's a method for adjusting parameter values to try and get the fit of the model better. Constituents. This is, I'll actually come back to these later because it's better to look at the soil. Let's look at the soils and the vegetation first. But this is going to be what's in what chemicals are actually getting modeled, like which particular pesticides, which pathogens, what organic material means, and initial values for it. So we'll come back to that. Hydrology. So these are various parameters related to runoff generation and evapotranspiration per HRU that are related to, but not exactly this. They're related to the soils and the vegetation properties, but they're a bit separate to them. So these are, I will actually come back to these, but these are adjustments you can make on top of the soil properties and the plant, the vegetation properties. They have to do with how water gets distributed within the soils, like between different layers, and how the plants can access it. So let me actually come back to those ones. But they're things that are set, they're parameter values that are set separately to the soils and the vegetation ones. And then these are the topographical properties that we mentioned before, slopes of the HRUs. Each HRU has its own slope. Yeah, and these are the floodplain ones again. So that's for surface flow. So these are hydrology properties that are a bit separate to the soils and the vegetation, but are linked to them. So sorry, I should have skipped those. So databases, so soils, and then the vegetation, but there are other databases stored under this databases section. But this plants database and the urban database are important ones for properties of HRU. So I want to actually start with the vegetation, and then we'll come back to the soils. So if you expand databases and we go to plants, you click on plants, you'll remember our model set up. In our case, we input land use with these short names. There was AGRL for agriculture, there was PAST for pasture, and there was FRST for forest. I hope people remember that. So SWAT comes with this big plants database. And you'll see AGRL is one of the vegetation names in the database that comes with the model. So this has default values for all of these vegetation types, and there are lots of them. Not all of them need to be in not all of them will be in your model. So these, and then if we have different vegetation types to the ones that SWAT comes with, we need to create a new entry into this big vegetation types database. I know some people said they've used ACRU before. ACRU has a vegetation types database built in as well for different South African vegetation types. And some of the parameter values in that are similar to some of the parameter values that SWAT uses. So when I've set up SWAT models for South African vegetation types, I look at some of the parameters that the ACRU database has and some literature on those vegetation types for South Africa, and see how different or similar they are to what SWAT has for the vegetation type. And I usually make a separate type. Either you make a new type, or you can modify an existing type in this database. You can choose how you want to do it. But when you make a new type, we need to add a new entry into this with a new 4-letter name, and then all these parameter values, and that would link to your land cover map that you would input to make the HRUs. So this has many, you can see how many, there's lots of pages in this. You can click down here to go to different pages in this database. And it thinks about it. It's actually not giving us the full name in this table, but I'll open a few of them to show you what kind of things there are. And it gives you, there's lots of, here we go. The description's all the way at the end. Okay, so if you scroll across at the bottom, you'll see the full names of all the vegetation types in this database. So different SWAT users. SWAT was developed by the U.S. Department of Agriculture and agricultural department, agriculture and hydrology at University of Texas A&M, but it's been used internationally a lot too. In different projects, they've added setups for different vegetation types people have modeled in SWAT. If you really dig into the values, some of them are quite approximate. And sometimes, like, there's 3 different types of spring barley. Like, people have added things for particular projects and then made it publicly available in this big SWAT database. But there'll be slight variations in them. Sorry, so if I go across, but you can start to see what there is. So so there's agricultural land close grown. So that would mean the plants are grown close together, densely grown. And then there's agricultural land generic, there's row crops, and then you start getting into particular crops. And the thing about looking at particular crops, there's values of like rooting depths and crop rotations and leaf area index cover and the evapotranspiration rates that will differ across these various crop types. There's quite a few different types of corn that will have different subgroups, cotton. So you can go through this on your own further, but if like I go to the next page, you can kind of see the different things they have. So there's various different kinds of forest that they have, evergreen, subtropical, dry forest, and all of these vegetation types, they have parameter values. So I'm going to open a few that are all in this table, but I'm going to open a few and we can have a look at what kind of values have been one needs to assign to each different vegetation type for the model to calculate all the things that it's going to calculate. So our model in this demo, in this tutorial, you'll remember it had AGRL, agricultural. So let's open up, I'm going to open up the ones, show you the parameters for the types that this demo model actually has. So it has AGRL. It's assumed to be a warm annual, so that has to do with the plant growth model. And if I pull all the way across, it's agricultural land generic. So it's annoying that they put the names all the way over there. So I will click on this editor button, and that will show me all those parameter values that are in the table, but it's going to describe what they are, the recommended value range, and what the value is in the database for that vegetation type. And then again, we can go to the help, and you could edit things. In this window, we could edit things and save our changes. You can also copy it and make a new vegetation type that starts with all of these properties and change one or two of them and save it with a new name. So that's what that copy is about. Yeah, so it has dataset value and your value. So if you change things, you would change them here. So some of the properties that it has, it's the ordering of them. Yeah, it's a bit arbitrary, but it has, oh, okay, N fixation. So like, because we do the nitrogen modeling in the soil, it needs to know if it's a nitrogen fixer. So some plants are leguminous, like beans and stuff, are going to fix nitrogen. So when you take nitrogen out of the atmosphere and fix them into organic form and add more into the soil. So your nitrogen in the soil will go up over time as the plants are there. So you need to say if it's a nitrogen fixer or not. That's a 1-0 parameter. This is about agricultural crops. And how about the growing cycle. So days to maturity, there's two different ways of looking at the crop cycle. You can use a days to maturity, or you put in 0 and it uses heat units. And with heat units, it tracks temperature. It's a way of doing things that's often done in cold climates as well. Well, you also do it here, but it's like the number of days that the temperature was warm enough for the plants to grow. If it got so cold the plant was dormant, then it will pause the growth. So then it uses heat units instead of number of days, because if it got too cold, it would pause. So that's why the heat units method sometimes gets used instead of just how many days the plant takes to mature. But this is going to assume these plants take 110 days to mature. And then there's things about biomass and harvest. If it's a non-agricultural cover type, one has to look at what some of these are as well. So there's things about this leaf area development curve. So this is all about a growth curve for the vegetation over the crop cycle, because it's an agricultural type. There's one thing that's also important for how much water the plants are going to use is the root depth, which is here. So this is assuming the maximum root depth is 2 meters. Because it has a growth cycle, it won't have roots of 2 meters all the time in the model. It will get to this maximum root depth once the plants mature. And then if they get harvested, the root depth will start again. There's a temperature for growth, so it's quite high in this case. Minimum temperature for growth, so if the temperature drops below this, it would stop growing or become dormant. And then there's nitrogen and phosphorus parameters. This parameter controls, this one is about stomatal conductance, and that's about evapotranspiration. So is this one. So this is about the humidity, how much water it's going to use at different points of water demand and the humidity in the air as well. So these ones, these properties, like if you're setting up a new vegetation type, my strategy would be to look at what SWAT has for different similar vegetation types or similar structures like grasslands or forests or crops of similar types and use those. But these ones control the water use, the rooting depth, and then the stomatal conductance, and then these control how the plant uses water as there's a higher atmospheric demand, and as water gets stressed, the soil moisture goes down and the plants get water stressed. Or these parameters. Some of these other ones, a lot of these other ones, we tend not to change too much, but they are about the nutrient cycling. But you can see there's a lot of them. Some of them are also, if you really want to model the crop growing, SWAT has an option to model crop productivity. And some of these, like if you actually want to get the yield of the vegetation as a crop right in the model, it's something people do with SWAT as well. So some of these parameters are more about that. But as you can see, there's a lot of values. Each vegetation type in your model needs to have all these values assigned. There are values in the database, and some of them I wouldn't look at changing. But if we find that our plant water use is way off, there are certain values one would change here. And you would also look at, is the vegetation growing and dying in the way that we expect on the ground? And if it's like the way we expect in our area in terms of like how maize grows and when it's harvested, similarly with sugarcane, etc. And we'll see that in the we can see that in the model outputs. And if that's looking not realistic, we would come back to these values and see what needs to get changed here so that the rate of growth and some of the management tables that I'll come back to about harvesting and stuff, are those right for the crop types? So that's this agricultural land, but all of these parameters, even the agricultural ones, are assigned to all of the vegetation types. It's just some of the values are a bit different to represent the growth cycles of the non-agricultural plants. So I'll just go back here because I'm not doing a change. But if we go, I'll just look at one other in terms of time. There was pasture and there was forest in this demo. So I'll go, I think we reach F. Okay, yeah, FRST. I think it's on page 3 in this big database. FRST is forest. I think it's forest mixed. So if I click on FRST, it's on page 3 in this database. And if I click on the edit button, we can see what the parameters are for that one. So it's perennial. That means it's not going to grow and die. Moist. Okay, so there's different options when you are perennial. So we can be a warm annual, a cold annual, or a perennial. And then the growth can be determined by temperature or moisture. In this forest mixed, this is the setup that they have. It's not a nitrogen fixer. Days to maturity, it doesn't matter because it's perennial, so it's not doing that. canopy height, so root depth is 3.5. So we saw with the crops, it was 2 meters. So we expect this vegetation type to draw water from deeper in the soil than the crop vegetation type did. And then the maximum leaf area index is 5. I didn't show you for the crop. I think it's about 2 or 3 there. Whoops. Oh no, sorry, my computer is having a... I'm connected to a remote desktop, as you can see, and it's lost it for a second. But this is a good section to pause. Is this making sense to people? Are you understanding what I'm talking about here? That we have land cover types, and every land cover type needs to have parameters for the model to calculate things like runoff and evapotranspiration for that land cover type. And this is where those values are. Is that making sense to everyone? Okay. Please do unmute and ask questions if you need to. The tutorial itself doesn't have steps that take you through looking at all of this. So obviously I'm not following through that PDF right now. I'm looking through, we're going through these menus to just have a look, see what's there, so you have an idea of what the parameter values are. So we've looked at parameters for forest, for this mixed forest, that general agriculture. I go back. And so there's this big database. So we'll have to think about what vegetation types one would represent in the uMngeni water catchments. Are they well represented by vegetation types that are already in this database, or are they close to some of them? And which ones? And what maps of vegetation types do we have to use? So we will talk about that in a future session, but this is an introduction to what the parameters are and where they are. So then there's separate tables for fertilizers. So these are different types of fertilizers. And you could set up your own type of fertilizer and what's in it. These are standard sort of tillage routines and how they're represented in the model. These are different pesticide options that have all the parameters for them, but you could also create your new, depending on what pesticide you wanted to represent if you're modeling pesticides. As I say, pathogens is not working at the moment, but will be added. And then the urban land cover types have some extra properties on top of the basic vegetation types. And so it has these inbuilt default urban options. This demo model doesn't have any urban types in it, but if it did, you could specify some of these, or you'd make up your own new urban type, or you could modify the parameters for them. So if I go into one of these, you'll see we can show you what these parameters mean. So for example, commercial area, they're assuming commercial areas. You have, if your HRU is classified in your land cover map as UCOM, instead we had that AGRL was the agricultural land, the forest was FRST. If we had a land cover type that was UCOM, it would consider it urban commercial. And so what that would mean is it would assume that every HRU that has that land cover type has an impermeable area that's 67% of the total HRU area. Of that, well, 62% of it is connected. When I say connected, it means like there's a, it's connected there's not pervious area like grass and soil in between the different impervious areas. The impervious area, the pavement's connected to each other, and maybe there's stormwater drains leading across the land such that the water from the impervious areas flows right off of it onto either to the stream or to the next floodplain land unit if we're doing it that way. Or if it is already in the floodplain land unit, it would flow directly to the stream. So in this case, it's saying 67% is impervious and 62% is connected impervious. So 5% is non-connected impervious. So that would be impervious area that has surrounded by vegetation or soil. And then curb length, I'm not sure what, I think that has to do with flow off of it. And then you have these wash-off coefficients in terms of if nitrogen and phosphorus and other things are getting deposited on the impermeable surface, how much it washes off when you have surface runoff off of it. You have solids building up. You have you can have concentrations of nitrogen and phosphorus in the suspended solid load so that's about this solids building up and wash off. So that can be things from like dust from car exhaust that can build up in urban areas and those kinds of things. And then you have, okay, moisture condition. Yeah, so that's about runoff generation. So that's 98% means there's going to be a lot of runoff for the impermeable parts of your urban areas. So again, if you need more help on these things, it's up there. So your different urban types will have different parameters for these values. So if I go back, you can see the fraction of impervious is higher for industrial. You have generic residential, but then they have different classes of residential, medium, high, and low. So like low density just has 20% impervious. They assume most of it's connected, and then these other values, some of them are the same across, some of them are different in terms of buildup of nitrogen and phosphorus, and then you could change them as you wanted. Are there any questions about the urban cover parameters? Good. So there are also parameters about septic systems one could add, and snow, which we're not going to play with, but we could. Yeah, so there's different kinds of septic systems one could add that have parameters around them if we're doing that have come from different projects people have been doing with SWAT, and they've added it to the global, like the database that comes with the model nowadays. So these are these databases. If we come back to the soil, so each of our HRUs has a vegetation type, be it the vegetation or urban. And then there's soils. So we had those two types in our map, right? The LX and the VRE, and it pulled from a database the different properties of these soils. So if I click on this soil type, it's going to show us the data that it brought in. Now, this one would prepare separately as a text file for the particular soil types you're going to use in your model. So we'll do this for the uMngeni water for which soils. But it has properties of the soil by layer. So this is layer 1, layer 2. So this soil has been defined with 3 different layers. And so if I were to click, and then here are some parameters for overall for all of the soil profile. So there's like the maximum rooting depth that's allowed in this soil is 1.6, which is the same as the total depth. So this soil is considered to be, this soil is assumed to be only 1.6 meters deep. 1,600, it's in millimeters. So if I click on a layer, we can look at the parameters. So if I click on edit for that layer, has the layer number, so it's layer number 1, depth to the bottom of the layer, 250 millimeters, so 25 centimeters deep, has bulk density, water holding capacity, saturated hydraulic connectivity, carbon, the texture of the soil, clay, silt, sand, rock. soil albedo, that's about how the soil heats up, the reflectivity of it, of light when it's not covered in vegetation. Is an erodibility factor for calculating how much is going to erode when it gets a storm on. Electrical conductivity, that's about saltiness. This will be about the pH, that's calcium carbonate, and also with the pH. So this would be assigned, we need to assign all of these to every soil type. There is the University of the Free State and University of Pretoria did a project where they made a database of these properties for the soil types in South African Agricultural Research Council soils. So we'll look at using that with some modification, but it has all of these values estimated for each of the soil types. So we can bring that in, but it's still rough because it's from a national, very coarse scale database. So if there's more local data that can improve how the soils are represented in our area, we can change that. So all the soils have these different, you can choose how many layers you want to include in the soil, and then the properties. So you can see like the bulk density of the soil actually goes down in this case. Okay, that's interesting. Usually it often goes up. So the top soil is higher bulk density than the lower soil layers. The carbon, as you'd expect, the carbon is higher in the surface soil and lower. Okay, so the clay is going up, that's why. The clay is going up as it goes down in this case, so that would make sense why the bulk density gets higher. So it's just that's the nature of this particular soil. And then we can look at the other soil. VRE. This one has also been defined with 3 layers. There's less clay in the surface. There's more clay going down in this case. Soil carbon is more in the top, etc. So you can see, and the water holding capacity goes down. The conductivity is highest in the top. So you can see what these values are, and you could change them based on information you'd have about your soils. You can also see how well the model is performing in terms of runoff, and you might need to change some of this for your soils. And then there's the nutrients associated with the soils, which is stored in the model in a different table. So there were some nutrient parameters in here. A little bit. Well, just the carbon, actually. Okay. And then the other nitrogen and phosphorus will be here. And then as you apply nutrients and as the plants on that soil add from the crops and from fertilizer applications, then the nutrients in the soils will change per HRU. But these are background soils parameters around nitrates and nitrites, and the carbon to nitrogen ratio and the carbon to phosphorus ratio. So that's where you would set, these are the places where you set the soils and the vegetation parameters that are very important for the model of this. These would be assigned to all your HRUs. Structural, yeah, this is about specific agricultural drains, septic systems, those kinds of things. So I won't go into that now. Water rights, you could also set some water allocation rules for when withdrawals happen. So we've covered the soils and the vegetation. As I mentioned, then these are parameters that are linked to how the soils and vegetation work, but they're set separately. But they can be a bit important. We tend to change them to help the parameterization, especially this ESCO1 and EPCO1. So I'll show you for an example what these are. Soil evaporation compensation factor, that has to do with Vegetation withdraws moisture from the top of the soil more easily than further down is the assumption in the model. But if you want to let it draw water from deeper just as easily, you can change that, and that will increase your evapotranspiration in the model. That's the plant water uptake compensation factor. And then the soil evaporation compensation factor has to do with how deep soil water can evaporate from the soil. So usually water that evaporates from the soil is just the water at near the surface of the soil. But if the soil is really porous or has a lot of cracks, water from deeper down can also evaporate. And when we have very hot climates, these parameters tend to become more important, and they determine how much water gets evaporated, which limits groundwater recharge and lateral flow and stuff. So we might be changing some of these. So these are over and above the specific vegetation types and the specific soil types. So I've introduced a lot of where the parameters are. There are other ones. Land use management is about, it makes a management file for each land cover type. So we had AGRL, forest, and pasture in this example. It will have a set of, so only the agricultural land is being managed with a rotation. These other ones don't have a rotation because it's forest. Okay, so it says commercial though, so it's commercial forestry. So maybe it is, and pasture. Oh, apologies, that's community, not commercial. Yeah, so the other ones actually aren't being managed. And then it has a curve number, which is something about how runoff is, how when it rains on this vegetation type, how much water runs off quickly versus seeping into the soil. So that's quite an important parameter. So I wanted to show you how, and that's assigned based on the vegetation type, but it's also assigned based a bit on the management and how the soil's tilled and stuff. So that's why it's here rather than necessarily in that vegetation database. But there is a value for it in the vegetation database, and then this one can override it. So I'm just going to show you that, because it depends if it's tilled or not. So it has this curve number. Okay, it's better to show it. Here are curve numbers. So the ACRU model uses a similar approach to calculating runoff versus infiltration, and so does HEC-HMS and some other models. They use this curve number approach, and the bigger the number is, the more runoff will be produced in a storm on this vegetation type. And there are tables of these by sort of the surface structure of the vegetation, where people have estimated these numbers. And so you can see the types and the treatments, like how the soil's been treated for agricultural types. So there's lots of options for different crop types and how the soil's treated in terms of assigning the curve numbers. And this has to do with the runoff during a storm. And this gets matched to your land cover type here. And you could pick different ones. And then there's also the Manning's N, so that's the surface runoff speed across roughness across your HRUs. So there's lots of parameters that you can change to represent how the land is being managed. This plant communities is when you can actually have different vegetation types occurring on a different HRU in succession. So if you wanted to make an HRU that has a rotation of like corn and then beans and then corn and then beans, you could set that up as a plant community, and the HRU could have a special name like corn beans or something, and then you could have, or maize, and then you would set up the rules of the rotations, and it would switch between those different vegetation types on the schedule that you set up. And and you have management schedules, which is about rotations. And then you have operations, and we'll have harvesting operations, irrigation operations. You can have chemical, so that would be fertilizer applications. It could also be manure. You can have burning, and then for urban areas, you can have sweeping. So again, I just want to show you what all is here, and then we'll, okay, grazing operations. So they have some default ones. Let me show you irrigation one. So you can have drips and furrows and sprinklers, and then you can make your own. So if I were to click on a sprinkler, this is a high intensity sprinkler. You can look at the efficiency, the amount, that would be millimeters per day. You can have, so that's, you can say that the sprinkler turns on, you can say if the irrigation is from a sprinkler, and then if an irrigation is from a sprinkler, it's going to assume that the efficiency is 80 and it can apply 40 mils a day. So you can change this, and then you can also change the rules of when it's off and on. You can also change, what concentration of things are in the irrigation water. So these are quite low. You could make them high if they think they mix fertilizer into the irrigation water. So this is just like irrigation types, but your schedules, here's where you would, you go into your management schedules, you'd add different schedules. So that would include, this is the harvesting. You could also add an irrigation schedule and a fertilizer application schedule here. And then this would be what are the components in those applications, and how is it applied? Does it land on the leaves? Does it land on the soil? That kind of stuff gets set up here. So we'll go into this more for our particular model, but I wanted you to know what all is in all of these tables, so you can start having a think about what all is here. And I'd like to encourage you to go through some of this on your own, especially with this tutorial model, because it won't matter. You can try editing things and stuff and see what difference it makes, or playing with numbers. It doesn't matter if you mess it up or anything. Because when we start working with the big model of the uMngeni water catchments, it's quite a big model with lots of catchments in it. And it's not as much of an easy place to play as this tutorial demo model. So I encourage you to look through all of these tables and get an idea of what's there. I've tried to show you the overall of what is there basically. So the next step one would do, after all of these are the way you want them to be, or you've done a run and you have an idea of what you want to change, you would go back and change these things. Then when these values are the way that you want them, you would go here, and this is running SWAT. And we're going to run it now, and I'll show you back to the tutorial. So when you go to the simulation period and you go to run SWAT plus, we're going to leave it as is. But we have to, and we left it default, we have to select set our simulation period. So we leave this part, choose where to write the input and output files. We leave it as the default. You can set your simulation period. So it automatically knows from now that we've input our weather data, it will have the simulation period that covers the weather data that we have. So 1990 to 2013 is the period it's going to run for. You can adjust within that period, obviously, but you can't run it outside of your climate data. So this, but just for the sake of the tutorial, they suggest changing it to 2000 just to make it a little shorter. And you might want to do that because maybe your data is better for that period. Actually, I'm going to make it even shorter so that the run is quicker. So, no, I'll leave it the way that it is. They say 2000, right? So it's going to run for 10 years rather than 23. So can they say, you can just type that in. You could also use the calendar selector if you want. Okay, the advanced options, the time steps are daily. Okay, if you were to do a smaller time step than that, it would make assumptions about how to spread things out over the day. And then this is the interesting part here. So we've left the where to write the input files. That's gonna, all these parameters that one might play with here, it's gonna put them into text files for our particular model. So that's why it's saying write your input files. So it's gonna take our choices, any changes we've made there, and write them into the text files it's gonna use in the calculations. And that all gets stored here. And then you set your simulation period. So that's how long the model's going to run. Oops, I didn't take my changes. 2000. Yeah, because you have to say, why didn't it save that? Oh, maybe I do have to use a calendar. Okay. Interesting. Thought it would change that. Let's see. Maybe it'll change it when I save. And then we're going to choose the outputs to print. And when it means print, it means save in a more easily accessible way. It calculates a lot of things, as I've talked about. So you don't have to save all of them all the time. And sometimes, so it'll calculate them whether you save them or not. But if you want to look at them easily afterwards, you want to have it print them to these various text files and databases. And that will take up space on the computer. So you generally don't want to print, you want to print enough to look at what you need to look at, but you don't want to print too much extra stuff. Sometimes you print things one run and then you don't print them the next run because you don't have, it's a balance of space on your computer and what you need to look at. So they do a suggestion here for the tutorial. So I will show you that on the screen. Oops. Here. So this warm-up period, this is how long you want the model to run before it starts. It'll run without saving the outputs. And that's because what I talked about with initial conditions. We're making assumptions about what the soil moisture is like and the groundwater and the water quality and everything on day one. And we don't always have good data to do that with. So sometimes the best practice is to let the model warm up, as they say, run with a sequence of rainfall, etc., for a couple of years before you actually start looking at the outputs. And they often suggest 3 years. So and the tutorial suggests 3 years. So you would put in 3. And then they're suggesting saving monthly outputs, yearly outputs, and average outputs. But so not daily for everything, but daily for channel. So channel, obviously, channel would be streamflow. So if you want daily streamflow data, you would need to save the daily outputs for the channels. So we generally do, if we're comparing to daily streamflow data, we want to save and daily water quality data. But maybe we don't need to know the water depth in the aquifer for every HRU for every day, but having a monthly average would be fine. So that's, or like for a reservoir, maybe we do want daily, but we don't have reservoirs in this model, etc. So you could choose which things you want to save the daily outputs for. So, and then there's nutrient, water balance, landscape unit, all of these things. So you could go through, and then this outputs, this tells you the name of the file, naming convention where it's going to be. And you could look at, in that input-output documentation website, you could see which things are going to show up in each one of these files and decide if you need them daily, monthly, or yearly. For now, we're just going to go with the setting options in the tutorial. So that's daily for the channel and monthly, yearly, and average. That's overall average for the whole run after the 3-year warm-up period for everything. So once you've got that, you would press I just want to make sure I'm doing what the tutorial says as well. You'd say you can do right input files are all checked. Yes. So you do save settings. So you make sure these are all checked. Write input files. Run SWAT plus. This is okay, there's a version that this debug version will run more slowly. It'll give you more warnings if you need to, but we actually don't need it in this case. And then analyze the output for visualization. So we would say save settings and run. So that first bit was taking all those parameter values we were looking at and assigning them to each HRU unit. And now it's doing calculation and it tells you what year it's in. See, it's doing 95. It's going pretty quick. Nice. And it's just going to read the output files back into those ones we told it to print. It's reading them. It's reading them into a database. So it took a while to talk through the various parameters. So we'll start looking at the outputs of this next week. But I think that is a good place to be. So hopefully if you're doing this on your own and you haven't been following along while I'm talking, if you could get your own projects to this point where you've managed to get it to run. Are people actually running it? Are people running it now while I'm talking, or have people just been watching me? How's it going, guys? Are you able to run it on your machine? Are you seeing what I'm seeing? Have I lost everyone? All right. Is anybody there still?
Yes, we are here, Joe.
Okay. Have you been able to get to this point on your machine? Is it running on your machine? All right. I haven't heard any. I hope you've been able to get it to run on your machine. Please let me know either way. And we'll pick up from this point next week. It's quite quick to look at the outputs, and then we'll move on from there. I saw somebody unmuted. Tanda, did you want to say something? All right. I hope everyone's managed to get to this point and have an understanding of what we looked at. Hi.
Open.
No, it was me. I was just saying, what if we are following behind you? We are not on the step that you are
Okay.
running right now, but we are following behind you.
Okay.
So,
Okay.
Yeah, thanks.
Okay. No, that's fine. I'm hoping so. Our next session is next week, Wednesday, the same time, and I'll go through how to look at the outputs. Sorry, I took a bit long going through the parameters, but as you can see, there's lots and lots of parameters for the channels, for the land cover types, for the soil types, etc. So I really encourage you to look through those, look through the documentation, and start thinking about how would you find those values or enter those values for the areas that you work in, to the degree that you know them. I mean, we'll use literature and defaults and stuff, but these are some of the decisions we have to make when we set up these models. So I wanted you to get a feel for that and an idea of all the things that go into it. But particularly what you might have inputs in are how different crop types are managed in your areas. Do you know the irrigation practices, the fertilization practices, those kinds of things? If you have general information on them, it would help to know that, because we can put that in the model to try and represent these non-point sources. So I wanted to show you where those things are, and you can start getting an idea of the values that are needed, and we'll come back to assigning them for the uMngeni water areas. Yeah, so I know it's a big, it's a big software program to get used to, but once you get an idea of it, and different people will work on different parts of it going forward, and as a team, hopefully you can get to a point of knowing how to edit it and run it as we go on. So I hope you guys have a good rest of the day, and we'll look at the outputs, look at the model outputs next week. Thanks. I'm going to say bye, everyone.
Bye, Julia. Thank you.